There is a force stronger than gravity, a force stronger than electromagnetism, and a force that ultimately deals with the tiniest scales of the universe. In this video, I'm going to talk about the strong nuclear force, a force that is responsible for atoms. We'll start from the basics, going over color, all the way to talking about asymptotic freedom. But this all starts with the basics. This is an atom. An atom consists of an electron, neutron, and proton. And these are the three subatomic particles that we learn in school. But what's really inside a proton? Well, according to theoretical physics, inside a proton we have quarks. And there's not just one quark, but there are rather three quarks, each of a different color. Now, quarks are the fundamental constituents of a proton. But how is the proton composed of these particles? So given the ingredients, and given the quantity of those ingredients, can we find the recipe to make a proton and a neutron? Well, let's take a look. So right now, we have three pieces of information. Number one, there are two types of quarks we can use, the up quark and the down quark. Two, there are three quarks in a proton, and there are three quarks in a neutron. And three, the up quark has a charge of positive 2/3 Z, and the down quark has a charge of negative 1/3 Z. So given these three pieces of information, can we find the recipe for a proton and a neutron? Well, the answer is yes. The proton has a composition of U, U, D, and the neutron has a composition of U, D, D. And we can verify this ourselves. The up quark has a charge of positive 2/3 Z, and the down quark has a charge of negative 1/3 Z. So we have positive 2/3 plus positive 2/3 plus negative 1/3, which is just 1. So the charge of the proton is positive 1 E. For the neutron, we have one up quark and two down quarks. So we have positive 2/3 minus 1/3 minus 1/3, which is just 0. So the charge of the neutron is 0 E, meaning the neutron is neutral. So right now, with these three pieces of information, we found the quark composition for both the proton and neutron. Protons contain up and down quarks, but the question still remains, how many quarks are there in nature? There are 6 quarks in nature, the up, down, charm, strange, and top and bottom quarks. The top row has a charge of positive 2/3 Z, and the bottom row has a charge of negative 1/3 Z, and all the particles are listed in increasing mass. What is color? Color is the type of charge the strong force acts upon. There are 3 main colors, red, green, and blue, and they add together to get white, which is neutral. So right now, at this point in the video, we still haven't answered the fundamental question. What keeps quarks together? And the answer is the gluon. Quarks constantly emit and absorb gluons, and this constant emitting and absorbing of gluons is what keeps them bound together. But there's a fundamental property of the gluon that makes it different from, let's say, the photon. And that property is the fact that the gluon itself has color. And because it has color, gluons can interact with each other. And that means that gluons can actually change the color of each of these fundamental quarks. Imagine we have a red quark, and this red quark wants to become a green quark. Firstly, it needs to emit a gluon. It has to emit a red anti-green gluon. The reason is because we want to preserve the color. Since we have a red quark and it's becoming a green quark, we need to emit that red color. But since we want to preserve that red color, we also need the gluon to have an anti-green color. Now let's say a green quark absorbs this anti-green red gluon. Then the greens will cancel and we'll just get a red quark. So we see that the colors have interchanged right here. Now that we've talked about quarks and gluons, let's talk about the composite particles that contain quarks and gluons. So imagine that this is a quark. The two main types of composite particles are particles that contain 2 quarks and particles that contain 3 quarks. Now, the particles that contain 3 quarks are called baryons. And in fact, we know 2 of these baryons, the proton and the neutron. And the proton and neutron are called nucleons. Now, there are also other types of baryons, which we'll cover later, such as the delta baryon, the sigma baryon, and etc. But now let's take a look at particles that contain 2 quarks. These particles are termed mesons. Now, one of the most common types of mesons is the pion, also known as the pi meson. The pi meson consists of 3 varieties: the pi plus, the neutral pi meson, and the pi minus. Now let me quickly go over the composition of each of these mesons. So the pi plus meson is composed of an up quark and an anti-down quark. The pi neutral meson has an up and anti-up quark, or a down and anti-down quark composition. And finally, the pi minus meson has a down and anti-up quark composition. Now, these pi mesons were originally proposed to be the mediators for the strong force, specifically the strong force between protons and neutrons. So the question arises, what's the difference between the strong force between protons and neutrons and the strong force between quarks themselves? So let's take a look at the strong force. The strong force is the force that keeps quarks together and is mediated by the gluon. So the question still remains, what keeps 2 protons in the nucleus together, where by electromagnetic repulsion they should just simply fly apart? The answer to that is the residual strong force. So what is the residual strong force? We know that red plus green plus blue must equal to white, but this may not happen completely the way we want it to inside of a proton. And as a result, this effect leads to the protons staying together inside the nucleus, and we call this the residual strong force. And this is the reason why we actually have matter all around us. It's because of the residual strong force, which in turn arises due to the strong force. Now that we've talked about the difference between the strong force and the residual strong force, let's go back to talking about baryons and mesons. One of the types of baryons is the delta baryon. There are 4 delta baryons, and they're composed of the up and down quarks in their respective arrangements. They have a spin that is half integer and greater than 1/2. One of the types of mesons is the K meson, also known as the kaon. There are 4 kaons, and they're composed of the up, down, and strange quarks, as well as their respective antiparticles. They have a spin of 0. Now, quarks are ubiquitous in nature. They're found in both protons and neutrons, as seen over here. But we can't see a quark by itself in nature, and the reason is due to a phenomena called quark or color confinement. Quark or color confinement basically states that the net color should be 0 or white. But if we take a quark by itself, the net color isn't 0 or white, and that's the reason why we can't see a quark by itself. Asymptotic freedom is one of the most counterintuitive yet intriguing phenomena in physics. It states that as the distance decreases, the strength of the strong force decreases, and as the energy grows, the strength still decreases. Asymptotic freedom won the Nobel Prize in 2004, showing its importance. Throughout this video, we've covered topics related to color, to quarks, all the way to quark confinement. But these are just the tip of the iceberg to quantum chromodynamics, the quantum theory of the strong force. Now, if you learned something from this video, please be sure to like and subscribe to this channel, which is Quantum Conjectures.